All right, I'm going to lecture on kind of the end of chapter 17. I didn't get a chance to post anything for solubility products, and then I want to post on precipitates. So kind of put it all together. So solubility products are similar as far as when we talk about equilibrium. So things don't always dissolve completely. And that's true for like weak acids and weak bases, but it's also true for solids that might dissolve in solution. Some don't completely dissolve. Sodium chloride, has a certain amount, and then at certain temperatures. Same thing for like barium sulfate here. So consider the equilibrium that exists in a saturated solution of barium sulfate. So saturated solution, that means you have solid present because you've dissolved enough, but you can't dissolve anymore, so you're going to have solid at the bottom, but then you have ions of barium and sulfate in solution at the same time. And equilibrium is where like some stay solid, some stay liquid, but they're constantly going back and forth, but they're going back and forth at the same rate. So the equilibrium constant expression for this equilibrium is KSP, and SP stands for the solubility product. And notice how the solid doesn't show up in this, so it's just concentration of the ions that are present. And obviously a solid isn't dissolved, so there isn't a concentration associated with it. So the KSP is not the same as solubility. Okay, so the KSB, solubility, is generally expressed as the mass of solute dissolved in 1 liter, so grams per liter, or 100 milliliters, or grams per milliliter of solution, or in moles per liter, so molarity. So, so we have this kind of relationship or connection, and solubility of a compound is usually grams per liter, and molar solubility is moles per liter, and molar concentration of ions, and we'll kind of get into how we might look at it. So the common ion effect, which we looked at a little earlier, so if one of the ions in a solution equilibrium is already dissolved in the solution, then the equilibrium will shift to the left and the solubility of the salt will decrease. So let's say you have barium sulfite here, and I've dissolved it, but I want to dissolve barium sulfite in a solution of, let's say, you know, barium chloride. So there's already barium in there. Well, that's going to make it so that less of the barium sulfate dissolves, and it's going to shift the concentration to the left. Okay, so let's look at other factors that affect solubility. So if a substance has a basic anion, it will be more soluble in an acidic solution. So you've got magnesium hydroxide here. Well, let's just go on. So substances with acidic cations are more soluble in basic solutions. So hopefully it's kind of just kind of straightforward, the idea that because a basic anion is going to interact with an acidic solution to dissolve more, and then opposite is true. So an acidic cation combines with a basic solution, you're going to get more dissolved because of the interaction between the acid and that basic substance, or vice versa. All right. Another concept is what are called complex ions. So some substances combine to make a variety of what are called complex ions. And they involve metal ions interacting with Lewis acids to form complex ions with Lewis bases in the solvent. So here you've got, so an example here is you have silver interacting with ammonia, okay, to form this silver ammonium ion, okay, and you've got a variety of other ones here. And complex ions we'll look at a little bit. They're just kind of the basic knowledge of them is probably more necessary than a real solid understanding, but we should probably spend a little time in class on it. So complex ions, formation of these complex ions increases the solubility of these salts because, so let's say you have silver chloride. Silver chloride is not very soluble in water. You add ammonia to it, and you start getting silver ammonium complex ions, and therefore that silver chloride starts to dissolve, and you get more of it kind of dissolving in solution, and thus by creating this complex ion, of silver ammonium. All right, amphoterism. Amphoteric metal oxides and hydroxides are soluble in strong acids and bases because they can act either as acids or bases. So certain substances can behave one way or another depending on the uh, solution. This one, so you've got the aluminum hydrate complex ion, and then you change the base concentration there, and you end up getting this aluminum uh, and hydroxide kind of combo there as far as dissolving it a bit more. So cations that can do this or are more likely to do this would be aluminum, zinc, and tin that behave this way. All right, so one typical way that we use the KSP is to determine or predict whether a precipitate is going to form, whether we're going to see a solid form in reaction and what that solid is going to be. So if Q, so in a solution, if Q is equal to KSP, and Q is like the quotient at that point related to the concentrations. So the system is, if Q is equal to KSP, the system's at equilibrium and the solution is saturated. You can't dissolve anymore. If Q is less than KSP, you can dissolve more until you get to Q equals KSP. And if Q is greater than KSP, then you're going to have a precipitate form. Some type of solid's going to form. Now this, and we'll actually be doing a lab related to this probably after spring break. But this is, so let's say you have this whole slurry, or you have, you want to determine what's in like an unknown solution. And the way that you're going to determine it is by using a variety of reactions to try to precipitate out substances at different, using these different different additions. You start with HCl. If you get a precipitate forming, then it could be either silver, lead, or mercury that's dissolved in solution. If and then you kind of go through the process of adding these things and precipitating out different substances to determine what the unknown is in there. And that is going to be it for today. That was really fast, and we'll be covering some of this stuff in class tomorrow. But yeah, there you go.